All right, this is Mr. Wakefield welcoming you back to section 7.6. We already did four problems in this section, A, B, 1, and 2. We now need to jump over to some new kinds of problems. Notice in problem C, unlike the first four problems we did in this worksheet, it has a cube root this time. The other ones have square roots that we've seen so far. Two major differences with a cube root radical inside of an equation instead of a square root radical like we saw before. First of all, instead of squaring both sides, of course, just like before, you have to get the radical by itself before you do that. But instead of squaring both sides, you would cube both sides because it's a cube root. All right, but you still got to get the radical by itself first. The other thing is that you actually don't have to check your answer when you cube both sides. In other words, when you have a cube root radical in your equation instead of a square root radical. All right. So just on the ones where you have to square both sides, that's when you got to check your answer. But since we cube both sides in a problem like this because of the cube root, you don't have to check your answers. All right. So let's go ahead and proceed here. Again, we have this thing we want to get by itself. If we pretend like that's a variable again, I'll call it y once again. We have y minus 5 equal to 0. All right, so again, wouldn't we add 5 over, just like we did in problem number 1? We would add 5 over in order to get the y by itself. And so in the same way, we would add 5 over in order to get the cube root by itself. Okay, so let's do that. And then, just like before, when you get the radical by itself, that's when you move on to the next step. All right, but because it's a cube root, we still put a bracket around the entire left side and the entire right side. That hasn't changed. But the difference is that instead of squaring both sides, which I almost did right there, I changed it, we are going to cube both sides. All right. And the thing is that when you cube a cube root, just like when you square a square root, the radical and the exponent cancel each other out, and you just get 4x minus 3 left over right there. On the other side, 5 to the third power is 125, and that results in just a normal linear equation that we've seen so many times. And let's solve that. If we move the 3 over to the other side, adding it over, we get 4x equal to 128. And then if we divide both sides by 4, x will now be by itself, okay, and it would be equal to 32, okay, and there you go. So that's how you solve a equation with a cube root radical instead of a square root radical. Now, just a heads up down here, you guys, when you see a bracket with an exponent next to it, as we saw back in 7.2, if you've got a fractional exponent, all right, whatever the base is, whatever the thing is that you're taking to that power, that whole thing goes inside of the radical. And then if the numerator of the fraction exponent is 1, you can ignore that. You can just take the denominator 3, and that becomes your root that you have, okay? It becomes your index number here that tells you what your root is. And so that would make it a cube root. So I just wanted to give you a heads up there that that problem number 3 right there is just the same thing as having a cube root. All right, it's just that they write it a different way there with the fraction exponent. But you can go ahead and convert that to a radical so that you can then do the same thing that we just did in problem C, okay? So I'll let you go ahead and do that in just a moment here since that's a numbered problem. And then, of course, we'll look at the answers after that. But in the meantime, flip your worksheet over. I got one more problem I want to do with you together. And for the first time, we have a problem that has 2 radicals in it. Unfortunately, and there's occasionally times when you can get rid of both radicals at once, but that's not going to happen here. So it says here in the first step here, you know, they said get the radical term by itself, all right, all that. But what does it say here in parentheses? It says if the equation if the equation has more than one radical term, be sure that one of the radical terms is alone on one side of the equation. Okay? Notice here that you have two radical terms being added together here. And the addition separates it into two separate terms. So this is two separate radical terms here. It says in the first step to get one of them by itself. Okay. If you've got two radicals being added together and that's all you have there on one side, just like if you have two normal terms being added together on one side, the way to get one of the terms by itself is to subtract the other one over. It doesn't matter which one you move over, all right? But got to move one of the... Oh, sorry about that. That should be a minus, not a plus. Okay. We're subtracting it over. And so it cancels that out. And we get square root of x plus 4 by itself now equal to 4 minus this radical I moved over. Don't combine those two terms because they're not like terms. Remember, a regular term and a radical term will never combine when they're being added or subtracted together. In this case, subtracted. Okay. They're not like terms. Now that I've got a radical term by itself, even if it's just one out of the two radical terms that's by itself, that's okay. All right. You now, again, put a bracket around the entire left side and a bracket around the entire right side. Okay, that's just to make sure that you're squaring the whole thing. But we do square both sides because, again, we're back to doing square root radicals now. All right, and the fact I'm squaring a square root allows me now to cancel out that radical that's on the left there. Square and square root, remember, cancel each other out there. But on this side, we got a whole other thing going on that's not easy, but we'll get through it. All right, remember when you got two terms... Okay, two terms, and we know these are two terms inside the bracket because of that minus sign in the middle that separates it into two terms. If we got two terms in a bracket and that bracket's being squared, it means we have to write it out like this. Okay. Now we saw that kind of thing in a previous problem back here in problem B, for example, and also problem 2 underneath it. But the problem is that instead of having just a normal polynomial inside of each bracket here, you now have some radicals in there instead. But it's not anything we haven't seen before. It just looks a little bit more complicated than normal here. Okay. But again, when you have two terms inside of each bracket, we do our normal thing here where you multiply the first term here by each of these two terms. And then you multiply this term here by each of these two terms. We saw this kind of thing back in the previous section, 7.5, where you had to multiply two terms times two terms. And we had some radicals involved there. Okay, we got used to that idea. We're going to do something similar here. All right, the fact that there's radicals there, it should not stop you from being able to multiply. So 4 times 4 is 16. 4 times negative the radical there. You can't multiply something outside of a radical by something inside. So these two things that I'm pointing at here, when I multiply them, they just smush together. We don't combine anything. We just say minus 4, square root of x minus 4. And then 4 times this radical, again, it's the same two things being multiplied. All right, so it's the same answer, minus 4, square root of x minus 4. And then finally, remember, negative times negative. When you multiply radical terms, you look at the outside of the radical to see what the sign of your answer is going to be. Negative times negative is positive, so I'm going to put plus there. And then when you multiply a square root radical times the same exact square root radical, that's just like squaring the square root, just like right here. Okay? Different radical, but the same idea. You're squaring a square root, all right, because you're multiplying the same radical twice. And so what do we get? X minus 4. Because when you square a square root, it cancels the radical. You just get x minus 4. Okay, now what you do at this point, like we did in problem B on the front side of your worksheet, we then combine, well, we didn't do that isolated there, okay? We actually moved the terms over at the same time. But you could combine like terms right here after you get rid of these brackets, all right? We're going to do that here in this current problem because in this problem was different because we knew it was a quadratic equation, so we knew we had to move all the terms to one side. But normally you would combine like terms first here, okay? But we just went ahead and did all that at once because we knew that we were going to have to move everything to one side anyway. This problem is different because this is not a quadratic equation yet. Whenever you got an equation, you guys, that has a radical in it, even if it's more than one radical, at least one radical with a variable underneath it, that's not linear or quadratic yet. You got to get rid of the radical before it becomes either linear or quadratic. All right. You got to get rid of, just like you had to get rid of the fractions before in a fraction equation before it became linear or quadratic. Same idea. All right. So I'm going to go ahead and combine like terms right here. I'm not going to worry about whether or not it's linear or quadratic because it's not either one of those things yet. Okay, so combining like terms right here on the next step, we can combine the 16 and the 4. That's going to be equal to 12. By the way, the other side stays the same. There's nothing to combine over there. That's just two terms that aren't like terms. And then the x doesn't combine with anything right here, so I'm just going to add that to what's already there. And then I get what? I get these two radical terms can be combined because when you add or subtract, in this case subtract, two radical terms that have the same radical, I get what? Okay, and I already started to write it down here. That's why I'm covering it up with my finger. I don't want to give it away too soon here. Excuse me. Negative 4 minus 4 is equal to negative 8. And so that would be negative 8, and then the radical stays the same. All right, like it always does when you're adding or subtracting radical terms with the same radical. The radical stays the same. Okay, so what we have here then is that after you clear out these parentheses, combine these like terms, and then what's going to end up happening is that you're going to have a normal radical equation now with only one radical in it like it was in the previous problems. Okay, so once you get those parentheses with the two terms in them, distribute them out, combine your like terms, you should then have one radical left if it's one of those problems that started out with two of them. Okay, you should have only one left. And then what you do, according to the directions, let's take a look. Previous sheet. It says if after all that, if there's still a radical in the equation, repeat steps 1 through 3. So we go back to the beginning, all right, and we do what? We have to get this radical term by itself. How do we go about that? All right. Well, we pretend like it's a variable again, just like we did earlier, all right, when we had just one radical term. All right. How do we get that y by itself? I need to first of all get the variable term by itself, and the negative 8y, I mean, and then you divide out the negative 8. The way to do that, since there's no brackets to clear out first here, all right, we already did that, but you got to move all the other terms over by adding or subtracting them over so that you have just negative 8y left, and then you can divide out. But if I do that, what do I get? I get the x's cancel, and I get negative 8, and then over here, all that's left is negative 8y. So if I then divide out, don't I get y equal to 1? Isn't that just y equal to 1 right there? So in the same way, if I move over, because you're going to do exactly the same steps, all right, when you move over, pardon me, when you are pretending like the thing you're trying to get by itself is a variable, you do the same steps in the real problem that you did to get that variable by itself. Same steps. That means to move over the 12 and the x's cancel again. We get negative 8 on one side. And then on the other side, instead of negative 8y, we have negative 8 times the radical because the y and the radical are the same. We then divide out, and sure enough, I'm sorry, I didn't mean to write y there. I'm thinking about the thing on the top there. It's similar to y, but that was just to show that As you know, the variable up there was just to show that it's the same thing as the radical, but we need to solve the actual real problem that has the radical in it here. The y was just to demonstrate that you can do it the same way as it would have been if it was a y. All right. But anyway, just like the negative 8's cancel right here, okay, negative 8's cancel right here, and you get 1 is equal to the square root of x minus 4. All right. Now, we square both sides. Why am I squaring both sides? Because I got the radical by itself. Okay, and it is a square root radical, so you don't cube, you square. But that's the idea, you guys. Once you take the two radicals and you do all these steps to break it down to where the equation just has one radical left, then you get it by itself again. All right, just like we had to get one of these radicals by itself originally, we now get the one radical we had left over. We get that by itself. Going back to step 1. Step 2 again is to square both sides after you get the radical by itself. And then now that there's no radicals left over, now you can ask yourself, hey, is it linear or quadratic? Well, it's linear because this is just x, not x squared, right? So that means to move the 1 and the 4 to the same side. Don't need to divide out because x is already by itself. And finally, after all that work, we got x by itself. Since it was a square root radical problem, all right, not a cube root radical problem, we got to check our answer. All right, plug it back into the original equation. Let's see what we get. Square root of 5 plus 4 plus square root of 5 minus 4. There we go, is equal to 4. True or false, you guys? True or false? Remember, you got to figure out the inside of a radical before you figure out the radical itself. So we have square root of 9 plus square root of 1. And then figure out the radical after you figure out the inside. And then you can add after you figure out the radicals. We get something that's true, isn't it? Okay. And so that means I can circle this since it's true. Okay. All right, so I'd like you to now try problems 3 and 4. And 3 was the problem on the front that's had that we converted to a cube root. All right, it had the fractional exponent. We converted that. Please try that. And also please try this problem right here, problem number 4. It's actually a little bit longer than the one we just did, so please be patient. Okay, but it's basically the same step, so it's just that there's one step near the end that's a little bit longer. But it's not anything we haven't already done. So do basically the same stuff here on 3 and 4, and then hit the play button, and we'll take a look at the answers. Okay, looking at number 3 right here. As we agreed to, this is the cube root of 3x minus 6. All right, so this is the equation we got. Once again, we want to think of what? We want to think of this as like a variable right here, because we want to get that by itself, the radical. So it's as if we have what? It's as if we have y plus 5 equal to 8. Just a normal little tiny linear equation like we've seen so many times. Y plus 5 equal to 8, so we got to subtract the 5 over in order to get the variable term by itself. All right, subtracting the 5 over gives me y equal to 3. Normally, after you get the variable term by itself, you divide out, but the y already is by itself. It'd be like dividing by 1, wouldn't it? Okay, because there's an invisible 1 here. But if we divide by 1, it's not going to change anything, is it? Okay, so that's the other reason why you don't have to do that last step. Not only because y is by itself, but because if I divide by the coefficient 1, it's not going to change anything anyway. So we do the same thing here, and we get 3 on the other side, just like I did here in this pretend problem that I wrote down. Okay, 3 on the other side. Because it's a cube root problem, I now immediately cube both sides, not square both sides, but cube both sides because it's a cube root that we have. I then get this right here. Okay, and then I solve that resulting linear equation that I get, and I end up with x equal to 11. Why did I circle that immediately? It's because on a cube root radical problem, you don't need to check your answers. It doesn't hurt to check your answers, you just don't need to. Okay, and if you did everything correct, you're never going to get a bad answer. Okay, if you did all your math correct and everything, you should never get a bad answer when you do a cube root radical problem where you're solving an equation with a cube root radical. All right, it's just the square root radicals that you sometimes get some bad answers, and that's why it's mandatory that you check your answer with square root radicals in your equations. Cube root radicals in your equations, not mandatory. All right, let's flip that worksheet over, and this quite possibly is the longest problem of the entire semester right here, you guys, so please be patient, okay? Waiting for me to go through this here. Just like on the problem D right next to it over here, okay, we have two radicals being added together, so naturally you're going to want to subtract one of those over to the other side, just like we did here. I went ahead and did 3x minus 7 subtract over, but you could have done the other one, okay, but since I did that, let's take a look at what happens. Now that I have subtracted that over, I now square both sides because I got one of the radicals by itself, all right? And that's good because then I'll be able to get rid of that one radical, and then ultimately, even though it won't look like it at first, I'll ultimately have only one radical left, and then I can get rid of that one next. So just similar to the last problem here, let's look at it side by side here. You square both sides. The side that just had the radical only, that radical goes away, just like with the x plus 4 over here. And then you multiply this out just like I did here. Okay, multiply it out in the same way. Okay, pardon all the color there. I was just emphasizing some things there, which I'll point out once again. All right, so multiplying this out, these are the things that I get right here. All right, just in the same way I multiplied this out. I then combine like terms just like I did here, going from this step down to this step. Okay, so I can combine the 1 and the 7. That gives me the 8 right there. The 3x, and you can put the 3x behind the 8, that's fine. You could say 8 plus 3x, but I just put it in front, all right, but it doesn't matter. But 3x didn't combine with anything, so it just comes on down. All right, and then notice that there's a negative 1 in front of each one of these radicals. So you have negative 1 minus 1, just like we had negative 4 minus 4. We can combine these radical terms that are being subtracted here. Negative 1 minus 1 is negative 2, and so that's why you get negative 2 with the radical staying the same. All right, now, just like we did in the last problem over here, all right, once you distribute and combine like terms and you just end up with one radical left over after all of that, now you get that one by itself. Same thing here, you get this one by itself, the 3x plus 7. How do I do that? Okay, similar to the problem, this problem over here. Okay, we pretend like that radical is a variable. See how I wrote down the same exact problem as I have right here? It's just that I changed the radical to a y. Everything else is the same here. Okay, so I do the same steps to get that y by itself that I did to get the y by itself over here. Okay, this is a separate sheet from where I originally did that, but this looks exactly the same here. Okay, as what we did earlier. So I move over the 3x and the 8, just like I moved over the 12 and the x in the previous problem over here. And then I divide out the negative 2. Moving over to the 3x and the 8, I get negative 2x minus 6. They do not combine, so we got a little bit more work to do here. If I divide out the negative 2, you've got two terms divided by a single term. We've seen that before. Two terms divided by a single term. Okay. You can divide that just like you would in an mx plus b problem. That's fine. Okay. And if you do that, you're going to get positive 1x, positive 3. So it's going to be x plus 3 right here. And there it is. X plus 3. Now that you've got the radical term, or not just the radical term, but the radical itself, you've got that by itself. All right. Now you can square both sides again, just like when I got the x minus 4 by itself over here. I square both sides again. This is going to be a little bit tougher, though, this time because I don't just have some single number over here. This time I got x plus 3. And as we learned earlier in this section, reminded ourselves of the fact that when you got two terms in a bracket separated by a plus, that makes it two terms, and you're squaring that whole thing. And yes, I got to put a bracket around this like we talked about when you square both sides. So two terms in a bracket being squared, you've got to do this thing right here, x plus 3, x plus 3, which then leads to what? That then leads to these four terms right here. And finally, I know it seems like it's taking forever this time. Finally, we got all the radicals gone. So now we can finally ask ourselves, now that the radicals are all gone, is it linear or quadratic? Well, this time it's quadratic because of the x squared right here. So let's go ahead and move everything to one side like we normally would, at least for the time being when we do a quadratic equation. All right. It looks like we're going to have an x squared term, an x term, and a constant term too. So get it in this order right here with the x squared positive. Okay. Those two things, again, are required for the Berry method. X squared positive, put it in this order right here. And then when I do the Berry method, I get these two brackets. Which means that now that I'm done factoring, I what? I set those factors equal to 0. We're almost there. And then I solve those. I get -2 and -1. But why did I cross out -1? It's because when I check the answer, it's going to be false. Let's take a look. Starting out with -2, why is that one true, though? That one ended up being true because we got, plug it into the original equation, we got the square root of 0 and square root of 1. -6 plus 7 gives me the 1 right here. Okay, remember after you do the insides of your radicals, you can then do your radicals, figure them out, and then you add at the end, because addition always comes after after evaluating your radicals. Okay, and this is true, isn't it? Okay. If I plug in -1, however, it's going to be false, isn't it? All right. You get square root of 1, square root of 4. All right. That then you evaluate your radicals before you add, and you get 3 equal to 1. Obviously, that's false. That's the reason why I crossed out -1. It's because it made it false. But -2 made it true, so I circled that one. So a very long problem indeed. Okay. But good practice, though. All right. And so the lesson here is when you got two radicals, okay, get one of them by itself and then go through the process of squaring both sides, and then ultimately you end up getting just one radical left over, okay, right here. And then you get that by itself, going back to the beginning and starting over by getting it by itself again, all right, this time just this radical getting it by itself. Then you square both sides again, and finally all the radicals are gone. Okay, so as usual, you guys let me know if you have any questions about this or anything else in this packet. And but that does conclude section 7.6. And you have a good day. Take care.